Today I'm going to look at a question about counting principles. The question reads as follows. A password for a safe consists of 2 letters followed by 3 single-digit numbers. Before I get into the questions, let me just represent this situation with a bit of a diagram. So because I will have a total of 5 spaces, because I have 2 letters and 3 single-digit numbers, I'm going to represent that by 5 empty spaces. 1, 2, 3, 4, and 5. Okay. So the first 2 spaces represents the letters, and the last 3 spaces represent the single-digit numbers. Okay, so let's get into the questions. How many different outcomes are there for the 3 digits if repetition is allowed? So I'm going to focus on the 3-digit numbers. How many different outcomes rather are there for the 3-digit if repetition is allowed? So we know that repetition is allowed and we are focusing on the 3-digit. That means I'm going to focus on the 3 spaces. So for the first spaces, we have the options 0 to 9 because they set single-digit numbers. Okay, so from 0 to 9, that means I have 10 possible options for the first space. Okay, for the second space, because repetition is allowed, I can repeat any number I chose on the first space. So I still have 0 to 9, which makes me remain with still 10 possible digits. The last space will also have 10 possible spaces. By fundamental counting principles, that means I can multiply all those to get the total number of combinations for the 3 digits. So the answer for this would be 10 power 3, which is equal to 1000. What does that mean? It means we have 1000 3-digit number combinations. Okay, we have 1000 3-digit number combinations. Therefore, the answer for A would be 10 to the power 3, which is 1000. Okay, so let's look at the second question, which is question B. How many possible outcomes are there for the 2 letters if repetition is not allowed? We're going to focus on the 2 letters. So repetition is not allowed. So that means for the first option, for the first space, I have any option between A to Z. So that means I have a total of 26 options for the first space. And for second space, if maybe I chose a letter A, or a letter A was chosen in the first space, that means for the second space, I have the options from B to Z. So that leaves me with 25 possible options. Another example would have been I chose B on the first space. That means I will still have 25 options because I wouldn't have chosen A. So that means by fundamental counting principles, the total number of combinations I have is 26 times 25, which is simply 650. So that means the answer for B is 26 times 25, which is equal to 650. This means that 650, we have 650 2-letter combinations. We have 650 2-letter combinations. So let's look at question C. So question C states, what is the probability of the combined outcome PR454 occurring if repetition is not allowed for the letters? So now repetition is not allowed, and we want the probability of the combined outcome PR454. Okay, so if E is the event that the combined outcome will occur, that means N of E is actually equal to 1, because there's only one possible way that PR454 can occur. Okay, So the total number of combinations we have for both the 2 letters and the 3 single digit numbers will be equal to n of s. In this case, s just represents the sample space. The sample space is just the total number of combinations we can have. So we can have 10 to the power 3 number combinations, but we can also have 650 2-letter combinations. So for the combined outcomes, total outcomes, we will have 10 to the power 3 times 650. Why are we multiplying? We are still using our fundamental counting principle. Okay, so this will give us a total of 650,000. Okay, so that means the probability of event E happening if E is the combined outcome PR54 will be equal to n of E divided by n of S, okay, which is equal to 1 over 650,000. Okay, so probability of event E happening would be 1 over 650,000. So let's look at question D now. Question D states, what is the probability that the first letter is not A? So in this case, I'm going to let E be the event that the first letter is actually A. Okay, I'm going to let E be the event that the first letter is actually A. So what I'm going to do, I'm going to look for number of combinations such that the first letter is A. For me to do that, I'm going to use my little trick of drawing empty spaces. In this case, I'm going to draw 5 empty spaces. 1, 2, 3, 4, 5. Obviously, the first 2 spaces represents the letters. Okay. In this case, the first letter has to be A. Remember, E is the event that the first letter is actually A. So if the first letter is A, that means on the second space, my options reduces from A to Z to B to Z. Okay, so that means I have 1 option for the first space and I have 25 options for the second space. Okay, but remember, repetition is not allowed for the letters, but repetition is still allowed for the numbers. Okay, so the last 3 spaces represent the 3-digit numbers. Okay, so I have 10 options still for the first space of the 3-digit numbers. I have 10 options for the second space and 10 options for the third space. Reason being, repetition is allowed. By fundamental counting principles, I can multiply all of that to get the total number of combinations. The total number of combinations such that the first letter is A will be equal to 25 times 10 to the power 3, which is 25 times 1,000, which is simply 25,000. Okay, so there are 25,000 combinations of password such that it starts with a letter A. The password, there will be 25 passwords that starts with a letter A. Okay, fantastic. But remember, we have a total number of outcomes, which is 650,000. So that means probability that event E will occur will be equal to n of E divided by n of S. Remember, n of E is the total number of combinations such that they start with letter A. So that is 25,000. N of S is the total number of combination, which is 650,000. So probability of event E occurring is 25,000 divided by 650,000. But remember, E is the event that the first letter is actually A. But in our question, we wanted the probability that the first letter is not A. So that means we are actually looking for probability of not E. Okay, probability of not E will therefore be equal to 1 minus probability of E. So these two are complementary events. So probability of not E will therefore be 1 minus 25,000 divided by 650,000. Okay, so if we punch that in our calculator, we can clearly see, let me just punch that in your calculator, 1 minus 25,000 divided by 650,000. We can clearly see that the answer is 96.15%. Okay, the answer for that is 96.15%. So probability of not E is 96.15%. Remember, not E is actually the probability that the first letter is not A. Remember, E was the event that the first letter is actually A. So not E will be the event that the first letter is not A. I hope that makes sense.